Hi everyone. In the second part of the tutorial, we'll develop the .dss file. In the first part, we selected the study area. We can see that's HEC-8, and out of this HEC-8, we'll basically work on this study area, this one, but we have to produce the input data set for HEC-8 level so that you can understand the real world case. So let me just show you what we have downloaded. We downloaded all the profiles here, including upper limit and lower limit of 100-year return period. So we'll utilize those to create 1% plus minus profile as well. And then we'll create the .dss file. That's the gridded rainfall input to HEC-RAS 2D model. So let me share my script. Here we can see that script is basically generates 1% plus minus rainfall precipitation. And let me show you the method. So here you can see we'll utilize this method. There are different methods as well. So here we just need to produce 1% plus, means upper 84% confidence limit. And you can see in order to do that, we need that 90% upper and lower limit. So those are the upper and lower limit we can see here from Atlas 14 NOAA data we have, and then we'll just calculate this medial rainfall and log and these and that, and you can see all the equations are there. So it will basically calculate all the parameters, and then ultimately it will save as the same raster we downloaded, but with plus 1% and minus 1% raster. So what I have done, I just implemented this methodology in my script. Here we can see I have the script there written there, and then it will generate two profiles. So what we need, we just need to assign where I have downloaded this data. So that's the download directory. So this is the only line number 13 you have to assign, and the code will take care the rest of the processes. So let me just show you one more time. So there is nothing. Let me just delete this one as well. I'm gonna remove this raster. So I'm gonna clean it up, deleting everything. There is nothing inside. If I go back, do I have anything here inside hydrology? No, there is nothing. So that's the input directory for all the profiles. And then I already assigned this location. And then if you just run the script, it will basically create those, and let's see how it works. It will take a few seconds. Let me just run it. It's running, and it's creating a necessary like folders, and let's see how it works. Yeah, inside hydrology, I don't know. Let's see if it is going to work. Still it's running because it's working on creating different geodatabase and also folders, and also applying the algorithm, the method I showed you there. That's why it's taking a while, but ultimately it should work. See, it extracted all the files, and then it will just start calculating because we use zip file. So first it will just unzip everything. It will just copy everything. So it took only 13.36 seconds to process everything. So here it created this folder, and then inside this folder, all pressive ASCII file, means it copied everything, and also it copied, see, it created 1% minus, also created 1% plus. This file has 3 different files, including .asc ASCII file, XML, and projection file. So it copied like every profiles, and also it calculated plus minus 1% and save it here. And yeah, so these are the temporary directory. It just extracted first and copied 100-year upper limit, lower limit, and median value. We don't need this one. We have everything here. So we'll use this directory to create the raster, like 6-minute interval, and we'll apply the correction factor. So in the next code I have, So what we need to assign the temporal distribution shapefile, the same shapefile we have the boundary, right? This boundary, we need these boundaries. So I'm just using the same distribution shapefile, and also area of interest means we need to use our study area. Where is the study area? Let me go back and find it. So from here, go back and GIS file, shapefile, HEC-8 projected, right? This one, we need the shapefile. So just copy that name because I know the directory is same as before. We just need to change the name of the shapefile. So now it's basically assigning our HEC-8 boundary, this entire boundary with red color. And then what we need that temporal distribution file, right? That master Excel file. Here, I saved it here. That master Excel file, you can see it's there. So it will just automatically intersect and find out the region, and then it will create a file. We'll see what it's gonna create here. So these are the input file we need. And if you just want to assign, because we're gonna process only for one day, it's 24-hour, you can use any date you want. Like you can use this one, or you can use today's date, whatever it is, it will just generate. Okay, let me just do that. So it's basically year, month, and day. I can even use today's date, and let's see. So it will just start generating the raster at 6-minute interval. And we use 1000 here. That's the precipitation scale factor, because in the raster file you saw it was basically 1000 of inches. So we need to take care of this. That was basically integer. So we need to use 1000 to convert it to floating number. So these are all in inches, and we'll have our rainfall data in inches. Okay, so if you just change only these 3 directories, and it will just process everything, and ultimately it will create separate folder for each of the profiles, 100-year, 1000-year, or whatever profiles we have, 11 profiles, and it will just save. Let me just run it, and automatically it will detect where is the study area and it is falling under which regions, and it will show you. So now it's falling under Texas B, Texas A, so it should print out that region here. So let me just run it. It will take, if you just want to process this one separately, maybe it will take several days, or even if you want to process it one by one, because it basically processing many steps. So it will take only 10 to 15 minutes. I don't know how many minutes it will take, but not more than that. Let me just run it. If everything's okay, then it will just print the region. See, it's printing that these are the region it's basically touching, but in general it's touching Texas A and Texas B. So let me just go back. Just reading everything there. Let me go back to hydrology. Inside hydrology, this hydrology, so it created this. See, it's also created this zone. All the zones it printed, it already got it, and then it's already created a subset of that, Texas A and Texas B, and it calculated the average. Then it will apply this average to calculate 6-minute interval of rasters. I think it's already started. It will save everything frequency passive raster for each of. So it started with 1000 years. That's okay. You can see it's giving you the date, and it's creating how many files it will create. It will just create 960 files at 6-minute interval. It's pretty fast. And after that, I'll show you what it is basically generating. I'll import one for you guys to demonstrate, because it will just clip. It will apply 5-mile buffer, and then yeah, so it's 900 file generated within like few Second, maybe it will take 1 to 1.5 minutes to finish one profile. So 960, it's done. That means it started another one. So it started this one. Okay, so what I can show you, I can just go inside and copy like one. Okay, this one I'm just putting out of this boundary to show you something. Okay, if I copy this and import it into GIS, and later on I'll just delete it. So this time you can see it's basically created the offset. Let me just load it. Maybe it's taking time to load. Yeah, see, it created a buffer. Previously it was the entire Texas. Now based on the boundary, I just clipped it, right? I just created a offset. And for factor of safety, I created a 5-mile buffer. So then what we'll do, we'll create .dss file. So inside this one, let me show you, like, yeah, it is still running for 100 here. Yeah, maybe it's almost done because we have 11 different profiles. So all the rosters are now basically at 6-minute interval. And then say this is also done. It started with -1%. So it's doing the same thing. And whenever it will be done, I'll utilize another script. Let me describe that script meanwhile to process. Like, this script will generate a DSS file from these rosters. So we have 11 different profiles. So your .dss file should contain everything. Okay, so what we need to do, we just need to assign the mother directory. I mean, this directory, this location where we have all the folders and 6-minute interval rosters. So it will just read everything, and you have to assign a destination, like a name of the .dss file, and this DSS file is called graded precipitation. That's the input to HEC-RAS 2D model. So whenever we'll create a 2D mesh using RAS mapper, and we'll refine the mesh using our road shapefile, we'll refine the mesh using our stream shapefile, and we'll assign Manning's calibration region because we have to use separate roughness for the streams. We have to use separate roughness for the overland. And then we'll even use culverts and bridges as cart lines. We have to find out if there is any dam. So we need to take care of all the features, and we have to make the model realistic. And after that, we'll run the model for one profile, like 100 year, and then we'll calibrate the model for 100 year profile because this is frequency storm and it has 1 day duration. But we are just distributing the total rainfall over the 24-hour period using 6-minute interval. So we're assigning the path because we know the .dss file, it has different path names. The first part will be any name, your HEC ID you can use, that's okay. And then part B, you can use your state, but part C, since it is precipitation, you have to use these. And here you need to use part Q, means within 6, because these are the rasters, right? It has 6-minute interval. So those are basically 6-minute accumulation. So we are using basically per cum, means the cumulative. And then unit is inches. So if you have any like different projected coordinate system, and if you need to project your raster as well, so here is the EPSG code. This is for different ones. So for NAD 1983 State Plan Texas Central, if it is Texas Central, FIPS 4203, right? So you need to find the PSG code. So let me just copy that and search for it, and maybe it will give you an idea about how to find out Yeah, so let me search for EPSG code for this coordinate system, and you can definitely get it. So it's showing like 2277. It's central, okay, 2277, and I think it's there, 2278. So we have to just change it as 2277 because it's just next to the zone. It was 4204 previously. That's why it was 4278. Now it's 4203. So we have 2277. So I have developed another set of scripts. Here you can see I just copied the script and I just save it as .py by this name. If I open it, yeah, let me just open and change that EPSG code. I just saved it separately. I have everything there, and 77. It's 7744203, but it's not South Central. It's only Central. I'm just saving it. So here I'm just assigning the roster, mother roster directory where I have all the profiles, and then I'm giving the name as this and where to save, and the cell size by default is 2000 meter by 2000 meter, means 2 kilometer by 2 kilometer. So it will basically calculate the frequency like year. For 100-year return period, it will just give you 1%. For 50-year, it will give you 2% chance. So this is how I have written the script, the way it will just create. So it will just loop through each of the directories, means folders, and based on this name it will calculate, and it will just add the profile, and you will see the process is very, very fast. But in order to do that, you need to have a Vortex. That's the executable developed by US Army Corps of Engineers. So what I'm doing here, I'm just trying to uh, like automate the processes. So you can just use the Vortex to import all the profiles one by one, but that will take time. You have to assign all the path for 100-year return period, 200-year return period, and for 11 times. And then you have to save it over and over, but you may make mistake. So no one knows. So in order to reduce the uncertainty or mistakes and to make the process fast, I've like automated this process. So if you just call this script here as bat script, I have everything inside this folder. I'm just calling it, and I'm also calling that Vortex. Let me find out where is the Vortex. Yeah, let me show you what I'm talking about inside this. Inside user, I think it's there. So this is the Vortex version I'm using. So I'm just calling this, nothing else. I'm calling, it has all the binaries and everything, the libraries. So if I just double click on it, whenever my processing will be done here, so let me check how many steps we are done. So almost we are done. So it's like, you can check it here. We're done with 8 profiles. So still we need to wait for a couple of more, minutes, and then we'll be done with all the profiles, and then we'll just hit that script. I'll just double click on this script. It will just call this script, and whatever condition we put there, it will just save the .dss file. And yeah, so that is the DSS file I created previously, and I can just skip that, and we'll see the process. And I don't need to save anything. That's okay. I can delete because I just demonstrated how it looks like. And I can just clean everything from here. I don't want to, yeah. I just want to clean my folder. So these are my download directory. I have everything there as zip file. The code already took care of this. it created the 1% plus minus, and it saved everything inside this folder. Now I'm running another script. It's calling and applying the distribution based on the intersection in between the distribution shapefile and the study area shapefile. And it's creating separate folder for each of the profiles, and it's saving the 6-minute interval rasters at T file. And then we'll just utilize this T file to generate .dss file, and we'll add the frequency name as well. So that is going to be the input for HEC-RAS 2D model. So we'll basically use this boundary as our study area to demonstrate. So you can even use this because that shapefile we saw, right? The raster was covering the entire Hockey, and we'll process our like everything for this Hockey. So you can utilize the same input file for every study area, like out of, yeah, we have 34. So you can just import and you can use the same file. And if you want to make one single model, you can just connect like using tie-ins. There are certain rules to apply the tie-ins, but we can see that later on. But now, whenever it will be done with processing this .tif file for each of the profiles we have, now we'll just generate .dss for this part. And later on, we'll even download that soil data from Sargo website, and then I'll even download the land use and land cover data to create the infiltration layer to create the gridded curve number, because that's the method we're going to use it here. And then we'll download the road shapefile. We'll download the stream shapefile because we already have the streams. And then we need to generate our nominal mesh, and then we'll refine the mesh following the stream shapefile and also the roadway shapefile as well. And we'll also try to download the observed data set. If we have any USGS observation, we can process that gaze data to calibrate our model, because this is frequency storm. So we need to compare 100-year simulation with 100-year like flow, or of course. So we need to either collect that data from regression analysis or from stream stat, or we need to do the gaze analysis. So we have different scripts to do that. If we need to, we'll explore together, no problem. I haven't even explore what data set we have, but if we find USGS, that's good. If we don't have USGS, we'll use regression analysis for this area, and I'll show you how to do that as well. So we'll calibrate after that, and we'll calibrate only for 100-year, and then we can just apply all the profiles. But I'm just gonna show you everything as a realistic project. Let me check the status. It's running. So let me check. Yeah, how many profiles we have so far? Almost done. The last one is running. I think it's 500. It's done. Which one is go to 5 years? Yeah, maybe it's done as well. So let me just check the script. Yeah, it's done. So how long it took? It took only 15 minutes. See, if you just want to process everything, it will take huge amount of time. So it created 960 file for its profile, right? So we have all the profiles here. We just need to copy this location, and then we have to save this, replace this location here. I already have done that, and then I saved it, and I know the name of the script here. So that's the name of the script, and then I'm just calling this script inside this. And if I just run that bat script, so here what I'm doing, I'm just calling that vortex, I'm calling other necessary libraries, and I'm just repeating the process. So if I want to save everything inside this BLE, we'll have our .dss file here. So let me just run it, and we can see. So there, double click on it. So it's reading, see how fast it is. It's just calculating based on the profiles we have as a percentage. For 100 here, it will just create 1%. You can see it 1%. And for 10 year, it's 10%, right? 50, yeah. So 2 year, 50%, and 500 year, 0.2%. Yeah, so that we have all the profiles, and it's done. It added all the profiles. And then if you just hit any key, it will be done. So you have your graded precipitation .dss. And if you just want to read it, you need to install HEC-DSS view. You can just download it from the HEC website. Even I have other videos previously I uploaded. You can even watch those videos to see. And here are the like pair, part A, HEC-8, part B, Texas precipitation, and that's the limit, right? Starting from 28th of July, 00 hour to 6 minute. And it's basically 0.1 means 1,000 year. If I select any like pair and click this plot, and it will show you that, yeah, same raster we just saw, right? Even with 5 mile buffer zone. So it's basically giving you the boundary outside of our study area. So that boundary is extending 5 mile outside of our study area. And if you want to see and animate, you can see the profiles here. 1,000 year is 0.1, and then at 0.2 is 500 year, return period 0.5, 10. You have all the 1% plus, 1% minus, 20, yeah, 4%, 50%. That's the 2 year. If you want to like see the variation, you can just click there, and then you can even click shift, I guess, and then yeah, click there. It will just load everything together. You can see that's the step. And if you want to see the animation, yeah, like this way, you can just click and you can see the changes. Yeah, you can see the changes. If you see the changes, that means it will be okay. Yeah, I think you can see the changes, right? The color is going up. That's the distribution within a day, you can see. Yeah, that means we have specially distributed rainfall, graded rainfall for this study area for all the profiles. So yeah, we are done. So that's the input to our HEC-RAS model. So this is basically the main input. And we need to even investigate our boundary condition as well. If we have anything coming from upstream, let me turn off this and let me see, because that's the stream. It's draining to this study area. So we have to use like here, right? We have to use an inflow boundary condition. We have to know the flow coming from upstream to this boundary. And we don't have any other inflow coming to this study area, but we have only one. And yeah, that's the way we develop our HEC-RAS 2D model. So in the next video, I'll set up the dummy model, dummy HEC-RAS model, and also I'll just create and like empty geometry, and also I'll process land use and soil data to generate the infiltration layer. So that's the second step. So thank you very much. Let me know if you have any question. That's it.